Okay. Hello and welcome you all in 4th Doctor of Engineering Conference 2024, Day 1, second session. I am Dr. Deepali Shende and Dr. Vishal Sharma, Faculty of Engineering Institute of Technology, is coordinating this session. The agenda of this session is, first, we will have an expert talk which will be presented by Professor Kalam. Then we will have Dr. Dibakar Rakshit's expert talk followed by student presentation. Now let us start with our first part of the session, that is expert talk by Professor Kalam. The topic is Decarbonizing the Australian Economy. Let me introduce Dr. Kalam. So it is my distinct honor to introduce Professor Kalam, a towering figure in the field of engineering and science, currently serving as the head of external engagement at the College of Engineering and Science at Victoria University. Professor Kalam brings with him a wealth of experience and expertise. With a distinguished career spanning decades, Professor Kalam has held key leadership roles, including Deputy Dean of the Faculty of Health, Engineering and Science for 7 years. His contributions extend beyond Australia, with the concurrent appointments as a distinguished professor at prestigious institutions such as the University of NSW in Sydney and various universities in India and Malaysia. As the editor-chief of the Australian Journal of Electrical and Electronics Engineering, Professor Kalam continues to shape the discourse in the field. His prolific research output, comprising over 500 publications and 29 books, underscores his dedication to advancing knowledge. A mentor to numerous doctoral students, Professor Kalam has guided more than 40 PhD candidates to successful completion. His influence extends globally as an external examiner for doctoral candidates in Australia and overseas. Professor Kalam's research interests span a wide range of topics, including power system analysis, communication, control, renewable energy, smart grid technology, and cogeneration systems. His multidisciplinary approach and innovative solutions have made significant contributions to the advancements of these fields. So please join me in welcoming Professor Kalam, a visionary leader, esteemed academics. So now may I request Professor Kalam, please proceed with the session.
Thank you very much, Dr. Shinde. Do you want me to start, Dr. Shinde?
Yes, please.
Okay. Can you hear me all right? I think you can see
Yes.
the screen, so that's
Yes,
all
we
right.
can. Yes, we can hear you.
Okay. As Dr. Shinde has already told about me to all of you, so there's no need of repeating everything. So I'll skip this slide. My content is very simple. I'll set up a scenario with an introduction. I'll set up the scenario with the introduction. Then I'll go to the outlook and predictions, look at the situations, then ask a question whether we can be 100% fossil fuel free. Then the role of alternative energy sources for decarbonization. And then my concept of having connected energy island and summary and conclusion. Now, before I start, I see that there are a few people here, and I would like to ask you one question before I start. Do you think, and this is to Christabel, Garth, Leon, Mike, Nimel, Paul, and Vitalis, can you tell me, do you think the topic that I've got is decarbonization? Is that the right topic? Do you think that we should be talking about decarbonization? What do you think? Can anyone answer me that? Anyone? Christabel, Garth, Mike, Nimel, Paul, Vitalis, anyone? No one game in that? No, it seems that uh, you're all shy. Anyway, I'll start myself. Everyone is talking about decarbonization. Everywhere that you hear, yes, Nimal says greenhouse gas emissions are due to carbon. Gard says yes, we should, or it could be phrased as moving away from fossil fuel. Uh, so, so it seems that there is some uh, consensus on decarbonization. And I want to start with the conclusion. The answer to both of them, whether it is Garth and the other person who said it, I would like to tell you that there is quite a bit of debate whether it should be decarbonization, it should be defossilization. I want to make it clear to you that life on Earth is carbon based, my friends, and carbon is everywhere. It circulates through the land, the ocean, and the atmosphere. This is what we call the carbon cycle. That is why the word decarbonization is a top notch misnomer of the top order. And I think that we should be talking about defossilization strategy. As I mentioned, there's confusion everywhere, in particular in Australia, when the government is bent on using the word decarbonization. And in particular, if carbon is the basis of all life, why is there concern about carbon emission and the push for companies to account for these? That is why I'm saying to say that let us try and see what is decarbonization. And that's why the first slide that I have is net zero versus decarbonization. If you look at that, net zero versus decarbonization. When we talk about net zero, someone mentioned carbon neutrality. And if you want to go for net zero, that means you remove all these emissions. And then I'll tell you at the end, by removing all these carbon emissions, your agriculture will go down the tube. Australia is a big agriculture country. All your packaging will go down the tube. You will have no one to do your plastic, your steel, your smelters, nothing, because it requires carbon. So be very careful. If you talk in terms of net zero, then you can say that we want to get rid of the greenhouse gases, which is the methane, nitrous oxide, and other hydrofluorocarbon, which is emitted to the atmosphere and is causing all these greenhouse gas emissions. So I've set that scene, and in Australia, our government had this net zero 2050 plan, and uh, it has been talked about it in number of sittings in the parliament. The government of Australia has made a legislation that they want to get net zero emission by 2050. And the long-term plan is to have net zero completely by 2050. So first in 2020, they said that we'll try to reach, and now the long-term plan is to have net zero by 2050. And therefore, they have said very clearly that they want to have an approach which is technology based, and they will like to protect all the industries, the regions, and the jobs. So, and I go back and set the scene. About 240 years back, when we had the first industrial revolution, there was a social paradigm and an engineering revolution. We had wealth and prosperity. And we were very much dependent on fossil fuel. Naturally, we were emitting CO2, and that is bringing in climate change, as you can see, and you cannot ignore that. And in response to that, governments all over the world have been talking about CO2 emissions so that the global warming is reduced, and therefore it should go down to 1.5 degrees Celsius. And you wouldn't believe it, the last COP26, which took place in Dubai, everyone promised, but no one has been able to do it. In particular, Australia has not been able to reach that target. Therefore, you find that the glaciers are melting in the southern pole. But the government definitely has responded by identifying key emitting industries. They've talked about CO2 targets, they've talked about industry policies, and they've said that they are trying to meet the international agreement, but it's not very much in the right track at the moment. So, one of the good things which has come, and that is renewable energy has come instead of CO2 based energy. You're finding more and more electric cars. You're getting battery storage system. I was reading the other day, 20% of Australia run a battery system in their house. So there is definitely a big push that by 2035, all our IC engine cars will be driven by electric vehicles. I can tell you before that, electric vehicle will become redundant and we will have to find something else because batteries are becoming a big problem at the moment. However, one of the things which is happening is the integration of renewables into our electrical system, and they are producing quite a bit of problems to our grid. Now, let us look at the situation. Everyone, as I told you, huge amount of investment is going to green technologies. And you're finding that even in spite of such a big amount of spending on green technology, besides rooftop solar, in which I can tell you, Victoria, where I come from, we have the highest intake of rooftop panel in the world per capita. But our decarbonizing progress is very, very slow. And we are 90% behind our 2030 and 2050 target. We have domestic storage and generation capacity, and they are needed to firm the renewables. It is said that if you have renewables and you do not have any batteries, then the renewables is not of much value. In particular, when you have got excess generation, you want to charge your batteries with that excess generation. I come from a different school of thought because I've got both the renewables as well as batteries in my home. And I tell you, the battery does not stack up. The batteries are not paying dividend. So we will have to come up with a new plan. And I don't know what the plan is, but we will talk about that towards the end. There is a plan that we should have large fleet of gas-fired peaking generation so that we can accelerate our renewable growth and have this close to the coal power on time. We should begin planning and development clean hydrogen infrastructure. A lot of hydrogen work is going on, including hydrogen storage. Then implement mandatory emission standards for all our road vehicles, starting with cars, supporting our EV charging infrastructure, particularly in underserviced areas. Now, in a country like Australia, it's very difficult to have all these EV infrastructure, charging infrastructure all over Australia. There's a lot of work to be done. A new CCUS scheme, which is carbon capture, utilization, and storage scheme, so that you can have a large scale usage. So, if you look at it and look at what has been found recently, this is a paper of 2022 by Vapla. You find demands differ drastically from 77 to 212 megaton per annum of hydrogen for 2030. And depending on the electrolyzer strategies, it will become 48 to 720 gigawatt of electrolyzer capacity. So we need that much electrolyzers to be able to cope up with that in 2030. At present, the global annual production of electrolyzer capacity stands at near 6 gigawatt. And how much we have to get? 48 to 720 gigawatt. And that is projected to rise to 20 by 2025. However, this increase falls far short of the demand, and there's going to be a big gap. The green hydrogen, which we are looking at, by 2050, we can only get about 148 to 660 megaton. So building a gigawatt green hydrogen plant takes 10 years, including 3 to 5 years for front-end design. So it's not so simple to do that. Now, as you have seen, if you look at this small thing that is there, this is the brown coal one. We are slowly and steadily finishing with brown coal. In my state, we have got a lot of brown coal. In Western Australia and Queensland, we've got coal, black coal. So we are phasing out the gas-fired heating and IC engine cars, but it has challenges. Look at the distribution grid. It's all becoming battery storage, right? And there is a huge amount of, for different studies, there's huge amount of potentiality for domestic as well as for exporting this energy. Now, if you look at it on building the hydrogen market, and when we look at this, we find that in the last 4 years, from 2017 to 2021, there were 25 country roadmaps which were looking for hydrogen. The countries which were interested were 9. Green hydrogen demand is about 15 to 30 megawatt. And you need 104 to 695 gigawatt. Remember, I told you can only get 20 gigawatt. And when we look at the gigawatt scale, we are looking at the manufacturing unit about 5 to 10 years. You need 39 electrolyzers, and the manufacturing capacity has to be greater than 20 gigawatt, as I mentioned. So the net zero, we need 200% capacity growth rate per annum, depending on the scenario that we are looking at. And there are various scenarios that we can look at, and these are the various scenarios that I've got, and all these various scenarios, if we look at various studies which has taken place, all the various studies that has taken place, you find between 2030 and 2050, the hydrogen, whichever studies you take, is not going to plateau. Look, it's all going up. It's exponentially growing. So these are the various scenarios of the demand estimations of hydrogen in the 20 years following 2030. And if you look at how many electrolyzers you need, and these are various studies done by various council, Energy Institution of Energy Australia, ARENA. If you look at that, you find that the 2030, based on various studies and operating hours that you find, you will find that it's all increasing dramatically. So you need to have huge amount of demand for hydrogen. Now, if you look at the installed capacity, again, there are 3 different scenarios I've got. This is one scenario, this is a second scenario, the third scenario. Look at the growth. The growth is growing exponentially. And therefore, it depends on which forecast you take. The first forecast has got 100% manufacturing capacities after 2 years, and the second is 50% of manufacturing capacities between 2022 and 2025 after 2 years, and 80% between 2026 and 2028. So it depends on the 3 market scenarios that I have talked about. But look at it, whichever you take, you find that there is exponential growth. Then let us look at the current situation. Those of you who know Australia, between 75 to 78% of our energy comes from fossil fuel. And to give you the example, 55% is from coal, Oil is less than 2%, natural gas is around 21%, something like 78% is coming from fossil fuel. Hydropower is very little. There's only one river in Australia, and therefore there's very little hydropower. They're looking at all sorts of pumping action, pump hydro scheme, etc. But it's so expensive. The last calculation they made, they were talking about $7 billion, and I don't think we'll be able to afford that in the time being. But the good news is that we're having a lot of solar panel installation, and that has increased. Wind turbine has increased. Bioenergy, unfortunately, is not taking up as much as I thought would take. So, so people are asking this question to the governments. What technology can add reliable? We are looking at reliability, we are looking at 24/7, we are looking at flexible base load power generation, and we want to do it in the shortest time. This is what people are asking. Then they're asking, which power generation technology can meet the joint criteria of timeline, sustainability, and cost efficiency from capital expenditure, operational perspective, and cost per megawatt? Cost. Cost is the most important thing. No project will succeed in Australia if the cost is not competitive with the coal fired plant. Should this new power source be held in private hands? Should they be publicly owned, or should they be assets held in public or private partnership, what we call PPP? According to that, should government declare power generation as a special class of essential service, enabling them to enforce decisions regarding these assets that more appropriately serve the public interest? So there are three basic things that are being asked: technology, what generation technology is there, and whether it should be private or PPP, and whether it be government owned completely. And if you want to look at it, the short answer to whether we can ever be entirely free of our need, and this is the question I asked, can we be 100% fossil fuel free? And I'd be very honest and very blunt, especially when we are looking at the naturally occurring hydrocarbon. The answer is probably not. The answer again is probably not. Look at that. I've written in red, probably not. And therefore, can we be 100% fossil fuel free? Probably not. And there are two reasons for that. And that is because of the naturally occurring hydrocarbons, which we collectively call fossil fuel. The most obvious use is powering everything from power plants and factories to smelters, and of course, fueling vehicles of every shape, size, and application. Apart from those countries that operate nuclear power facilities, even our electric trains, trams, cars, and buses are for the most part recharged by power generated through the consumption of fossil fuel. Now, replacing such type of fossil fuel, which we use in these energy-centric application, is an easy task. However, when we did our analysis, easier is a relative term. Nothing in this endeavor is easy, simple, or cheap. And I can tell you, my data suggests that there is no quick fix. Therefore, the other side of our reliance, and this is the important side, which the governments have forgotten, which for most of us is the least obvious, is the central and currently irreplaceable role they play in the production of materials. How will I get the lubricants? What about plastic? What about carbon fibers? What about adhesives? What about fertilizers and countless other substances that keep our modern world running? In this area, material production, naturally occurring hydrocarbons cannot be replaced. So we need those hydrocarbons. That is one of the problems that we have. So consider for a moment a society without the food produced by large scale agriculture or without water and sewerage processing. You know that those of you who don't know should know Australia is a great agriculture country. Our biggest export is agriculture. How will we replace all those technology marbles embedded in our life, like the internet, the computer chips, the laptops, the smartphones, the television, the air conditioners? Even the basic clothing that you are wearing, your housing equipment that you have got, cannot be produced without the derivatives of natural hydrocarbon, which is fossil fuel. Indeed, it's almost impossible to identify any manufactured product without a host of fossil fuel derivatives or feedstock for its production. By extension, and perhaps the greatest irony is that without fossil fuel derivatives, even devices like solar panel and wind turbine cannot be produced. We are dependent on, I told you, on renewable. You cannot produce these devices, solar panel and wind turbines, if you do not have these fossil fuel derivatives. So we got a bit of a problem. So imagine a future where we bridge the gap between our current energy system and a sustainable hydrogen based economy. The transition will bring numerous benefits, such as replacing every electricity generating facility that is not currently able to operate on or transition to a hydrogen based fuel, synchronizing the expansion of our green energy generating capacity by phasing out fossil fuel use across the entire economy, retiring every the 20.1 million motor vehicles that we have in Australia in favor of battery or fuel cell powered vehicles. We want to do that by 2035, just for your information. Retiring every diesel electric railway locomotive not capable of operating on hydrogen or an hydrogen based fuel, that is ammonia. Ensuring that every aircraft in the country can run on batteries or hydrogen based aviation fuel, and phasing out and replacing every smelting plant or manufacturing system that cannot transition to an hydrogen based fuel. Just imagine that future, and just imagine how you're going to overcome that gap. So, if we are to decarbonize our economy, the first step is to quantify the task and establish a reasonable path to accomplish our goal. At the macro level, that might mean setting up the electricity generation to transition to renewable, including hydrogen fuel. That's the easiest way. Let us remove all the fossil fuel plant. Let's make it everything renewable and hydrogen. First, we do that, and then we transition the rest of the economy. Okay? There are very limited ways of producing energy. And remember, it's not only producing, you might come with the best technology, but if it's not cost effective, it's of no use. No one is going to use your technology. So we have to make sure that we can produce energy at a price that we can afford, at a scale that meets the whole of economy application. There are 5 ways you can do that. One is by using nuclear fission that is propagated in a reactor. The second method is using chemical combustion, that is burning wood, dung, peat, coal, oil, gas, hydrogen, or ammonia. The third is to use chemical reaction, that is hydrogen or ammonia fuel cells. The fourth is to use direct kinetic energy harvesting, that is using wind or waves to spin a turbine. And the fifth is to use direct radiant energy harvesting, that is solar panel or geothermal tapping. These are the 5 ways you can improve it. Okay? So, if you want to make everything to replace all our energy generating equipment, I need about 100,000 wind turbines, about 50,000 offshore turbine, about 2 billion solar panel, or 800 gas turbine. And look at the cost. We are talking about cost between $825 billion to $2.3 trillion. Look at the annual cost too is $11.4 billion to $62 billion. Huge amount of cost. And if you got solar panel, you need to have 4,400 square kilometer of land just to put the solar panel. So we've got a big problem, my friend. Now, what's the path forward? I've given you all this gloomy picture. And let us start with Victoria. I'm only looking at a small part, this small part, Victoria. Victoria is Australia's second most coal-reliant state. 68% comes from coal energy. And the coal that is used is brown coal. I don't know whether you understand the definition of brown coal or not. I have my definition of brown coal. I say brown coal is, it looks like shit, it tastes like shit, it smells like shit, it is a top class shit. And we are using coal in Victoria, which is brown coal, for producing energy. You must give credit to the Victorian engineers who are using this brown coal, which cannot be used anywhere, to use it for producing energy. There's one downside. Okay, it's one downside, and the downside that I see is that it produces a lot of carbon. And there's also about 27% that's coming from renewables in our state, in Victoria. Now, my theory is the connected energy island concept. And I'm looking at the completion of a full-scale hydrogen production facilities. We will put that in place, the last of the key element needed for a successful implementation of Victoria's connected energy island concept. So I need a ready supply of first phase of fuel cell, which can power new high efficiency natural gas or hydrogen gas turbine generators. The promise of short to medium term availability of hydrogen fuel cell in proximity, easy access to the main grid infrastructure, substantial land, and a local government and community that is favorable. Because unless and until there is a will of the government, we will not be able to do this. So if you look carefully, this is my concept. I've got my national grid, I've got wind and the battery energy storage system. There I've added that hydrogen. There is my, in the middle, I've got my hydrogen. That's my hydrogen. This is the base load. Then I've got again solar base and hydrogen, and is going to the national grid. So that is the island concept that I'm talking about, that is all connected to one another. Look at that. There are no nuclear. And I want to mention it to you that there is no nuclear. The reason we have no nuclear, because in Australia we are nuclear free zone. We do not have any nuclear plant, with the exception of an experimental plant in Sydney, in Point Lucas, Lucas Heights, that we have got one. But that's a 5 megawatt plant. It's an experimental station only. It's not for power production. Australia is signatory to that, and to change the legislation would be impossible. But something has to be thought about. Should we be going for nuclear? Remember that 5 things that we talked about. So should we be going to nuclear? So I tell you that Net Zero Australia, they're all behind the decarbonizing technology. We have got everything going for the rooftop PV, no doubt about it. Australia has to move away from coal-fired power station Don't get me wrong. I am completely a very big supporter of renewables, and I think that we need to get out of that coal-fired plant. Remember, our coal-fired plant is a base load, so we have to look for gas turbines and high integration of renewables. We have to go to green hydrogen. And this is very frustrating. I'm working with ammonia at the moment. I'm looking at non-thermal plasma to produce ammonia on large quantities and with large, but it requires a long construction time, and there's a need of a manufacturing capacity. So, despite all these influential individuals and organizations that developed countries around the globe should eliminate fossil fuel use, but you have to be man enough or person enough to face the reality that our current suite of technologies need to be revised. Attempting to run an entire economy solely on renewable platform is trying to manufacture steels with candles. You'll never be able to do that. Eliminating the use of naturally occurring hydrocarbon is that some 99% of all our manufactured product which relies on them as feedstock rather than fuel. Hydrocarbons are the essential and currently irreplaceable raw material, enabling the production of practicality of all our plastics, lubricants, adhesives, and fertilizers. These are fundamental to produce the bulk of our food and manufacturing virtually every product or services that we take it for granted. So, I am not telling you, I want to make it clear that you understand this. I am not telling you that we should not go to the path of removing all our fossil fuel plant. I'm just telling you, let us attempt to walk more gently on the planet that we all share. However, the steps we take regarding climate action must be calculated and considered. The governments which makes blank promises, they must be aware of the potentially enormous financial and human cost that rushed and poorly thought out climate centric decisions can impose on their citizens for future generations. So, in the end, I want to mention to you that I started this program with an introduction, and I told you, is my topic right or wrong? And no one answered that. I asked, should I be saying that we should be talking about decarbonization or defossilization? The answer to that question, I'm giving you the answer right now. The answer is that we should be talking about defossilization, not decarbonization, because decarbonization is a misnomer and it is wrongly used. Every government, including the Australian government, is using the terminology uh, decarbonization because that's what they use in political atmosphere and a political realm. And that's what we keep on hearing and be bombarded in our mind about this decarbonization. And I end with a quote from Abraham Lincoln. The best thing about the future is that it only comes one day at a time. And if you want to read more about it, I have written a paper on that. And you can see that paper. It's a Journal of Engineering by IET. It is at the moment, there is a version which is in the journal itself. If you type in my name and talk about decarbonization, you will find that journal paper. With that, I have finished my presentation. I'm open to any questions. So, Dr. Shinde, can you switch off this
Yeah,
slide yep, so I
yeah,
can see the people and then we can talk to people.
yes. Uh, yeah. Thank you, Professor Kalam, for this insightful presentation and emphasizing the decarbonizing the Australian economy. So here, at least we understand that decarbonizing the Australian economy is not only essential for climate change, but also offers a multitude of benefits for participants across various sectors as well. So now I request participants, if they have any question or any comments, please feel
There-
free to ask here.
There's already questions on the chat session. If you
Okay,
look
let me
at
check.
Paul,
Yeah, sure.
Paul has written a very good question,
Hmm.
and uh, and he's talking about inefficiency in producing green hydrogen. This is something very interesting. It is not inefficiency in green hydrogen, Paul. It's inefficiency because we are talking about a very low temperature and the usage of the gas pipeline that is not only storage but transportation could become a big problem. In Australia, what we are looking at is exporting these through the existing gas pipeline. Uh, uh, yeah, and I don't want to read your last paragraph, which is very interesting. Um, yes, I agree. Combustion is a very big issue, and therefore, Shasha has asked a very difficult question as usual. She always asks difficult ones. Um, which country is leading in terms of decarbonizing technology? The only one that I can think about is the United States, and they're using nuclear. And they have that added advantage, Shasha, Dr. Wang. That's the advantage they have. And there's a huge amount of conversation in the Australian scenario at the moment that should we be re-looking at the nuclear debate again and try to get it in the United States in looking at various domestic usage. They're using those smart uh, small reactors in their homes, which is at the outside where they have placed their batteries and their gas heaters and all. I can tell you right now, Dr. Wang, that in Australia also, in particular in Victoria, we will be coming to a stage when we'll have to get rid of all our Victorian houses, which are designed for gas heating purposes. We have to come with a different technology. I hope I've answered your question. Christabel is asked, have you included social engagement? Absolutely. In Australia, we can't do anything if there's no social engagement because whether it is carbon emission, whether it is nuclear reaction, if I have done this many times and I've asked people what is the best source of energy, what's the best technology that you've got, and they all keep on saying that the best technology they have is the nuclear one. But then I say, do you want to have a nuclear plant adjacent to your house? Everyone says no, no, because they're scared of the emission. So that's the radioactive emission. Uh, so, yes, and the question is that how do you plan to reach to such communities? You have to do those surveys. Um, uh, okay, Garth, hello, Garth, good to see you. Um, I think he's asking questions on nuclear, whether from technology point, is it part of the solution? Do you think it'll twin well with the variable supply? Absolutely. Renewable is uh, absolutely complementing the nuclear technology. There is a problem, I agree with that. We are talking about fission or fusion. You have to be careful. If it's a fissionable one, then it is very, very possible, and I think the community will accept it too. And I can't see any more questions, Dr. Shende. I tried to answer as much as possible, as quickly as possible, because I'm running a bit short of time. Only have 1 minute before the professor from IIT will start.
Okay, thank you. Thank you so much, Professor Kalam, for providing the answers of all questions. And also, I would like to thank all participants for their active participation. Thank you. Thank you so much, Professor
Thank
Kalam.
you very much,
Yeah.
Aarti, and bye bye.
Hmm. Bye. So, now moving ahead with the next expert talk, which will be presented by Professor Dibakar Rakshit. The topic of this expert talk is grid scale thermal energy storage. I would like to introduce Dr. Dibakar Rakshit. So, Dr. Rakshit is a distinguished professor at the Department of Energy Science and Engineering at the prestigious Indian Institute of Technology, Delhi. His journey in the field of energy science began with his PhD studies at the University of Western Australia, where he developed multiphase mass transfer phenomena, particularly focusing on thermal diffusion of liquefied natural gas. During his postdoctoral research at Australia, Dr. Rakshit's focus shifted towards characterizing the thermal behavior of solar receiver heat transfer fluids, crucial for power generation. This marked the beginning of his deep engagement with thermal energy storage, a field he has since pursued relentlessly. Upon joining IIT Delhi, Dr. Rakshit continued his exploration of thermal energy storage, particularly in materials applicable to building energy conservation. His research trajectory then evolved to include nano-enhanced phase change materials for thermal energy storage in building envelopes. So, alongside, he has contributed significantly to the design of energy efficient buildings, sustainable building infrastructures, and the development of technologies addressing social energy needs. Dr. Rakshit's groundbreaking research has garnered support from various national and international bodies, including the Department of Science and Technology, Ministry of Education, DRDO, and numerous private sectors. His leaderships extend to significant projects such as the design and development of grid-independent solar-assisted vapor absorption systems under the Indo-Toronto program. His dedication to research excellence and his role as a mentor to numerous students underscore his profound impact on the field of energy science and engineering. So, here, please join me to welcome Dr. Rakshit, and may I request Professor Dibakar Rakshit, please proceed with the session.
Thank you. Good afternoon. Good afternoon,
Good
all of you.
afternoon.
Good afternoon, professors, and good afternoon, the participants. Thank you for giving me this opportunity, and I feel very overwhelmed to again uh, come back as an academician through this presentation to Australia, because that's where I started developing my interest in the area of multi-vector energy systems, and then going ahead more specifically with energy storage. So that's why I'm very much indebted to the country. And so without wasting much time, I think I will start with my sharing of slides. So I think my screen is visible. Professor?
Not yet.
Acha, just a second. Just raise hand, my status. Where it is basically to show the screen sharing, I'm not able to uh,
Um, right hand side down. So, maybe beside the attendee list and this chat
yeah,
box. Yeah.
activity list and then share content, is that the
Mm,
one? Mm,
yeah.
let's just check a second. Share application screen. Yes, there you go, thank you.
Not able to see it, but
Yeah, now I have shared it. Is it visible now?
uh, yes, whole screen we can see now. Yeah.
You can see, right? So I will
Mm,
just put it on the
mm. Yeah, now able
here.
to see.
Yeah, so thank you for helping me out with this screen sharing thing. So yeah, today's talk will be more on thermal energy storage in specific, if I have to say, and then what is the utility of thermal energy storage. First, I will give some brief idea of energy storage, and more specifically for thermal energy storage in grid scale system. So that's what I will be talking about. So this is the list of content for today's presentation. Now coming to uh, coming to the system where this energy storage becomes the central theme or the moot point when we are trying to connect various energy vectors. So if I'm speaking about microgrid or small scale generations, or if I'm speaking about mega grid or mega scale generations, every time nowadays we are speaking about energy transition, or we are speaking about the hybrid type of system where both renewable and non-renewable will be working in tandem with each other. So when we are speaking about this sort of arrangement where grid penetration through renewables is happening, where we are trying to understand how both the system, means the renewable and non-renewable, can coexist, one important point of this multi-vector system is energy storage. And this entity of energy storage actually helps us to connect all those multi-vector system, which helps us to transmit energy, which helps us to utilize energy at a particular point, at a particular time of the day. Where I'm why I'm mentioning about the time of the day is that because there is a diurnal variation, there is a limitation through which the renewables can be utilized. There are seasonal variations, there is the revolution of the earth around the sun. So basically, to capture those uncertainties which are associated with this renewable form of power generation, can some way or the other make us to understand what is the significance of energy storage. So now when I'm speaking of energy storage, the first things which comes in our mind is batteries. So battery is that same terminology which we have studied, which we have listened through, which we have designed for ages. But now it is actually crossing the boundary where we are not just speaking about electrical batteries, we are also speaking about thermal battery. The concept is same, where we store energy and then we retrieve the energy as and when it is required. And that's how this new terminology has been coined out, which is known as thermal battery. So I think this much of introduction to the importance of thermal battery is more than enough, that why we are venturing in this area of energy storage, where thermal energy becomes the main point of discussion in connecting various multi-vector energy systems. So if I'm speaking about energy storage in generally I chalk out this definition when I teach this subject, energy storage, in the class. So and this gets evolved out eventually over a period of time, because there is no such specific definition when we are speaking about energy storage. So starting from the very minimal requirement of energy backup which we have in our UPS, uninterrupted power supply, to the material aspect which is associated with the resilience of that particular battery in which the energy is stored, whether it is the low grade thermal energy or high grade electrical energy. You will see that there are many dimensions over which you will find the definition of energy storage is spanning. And the main thing which comes out over this keywords through which the energy storage definition can be coined out, it is to fill the gap between the supply and demand. And that's what we say, that when we want to cater to the demand side management of the prosumer, in fact we are not consumer anymore, we also produce energy locally when we speak about microgrid. So in fact, to fill that gap between what the actual energy demand is and what the grid can supply, to maintain that energy demand gap to its minimum possible level, energy storage becomes the moot point of study. I will not go in details of each and every keywords which is highlighted over here, but basically the main point over which this energy storage or this thermal battery or electrical battery is conceptualized, it is just to provide backup and just to cater to the need of our power requirement as and when it is called for. So let's just try to understand a bit more on the demand side management. So if I'm speaking about the power requirement, basically it is not same throughout the day. Basically it is not same throughout the year. there are certain time of the day when there will be huge surge in power requirement, and there are certain time of the day which will be lull enough to not utilize the power what is actually getting generated. And there is certain mismatch because of this requirement of power at certain time of the day and during the other time of the day where we can have the actual generation. To cater to this requirement, the concept of peak shaving is being conceptualized, where we want to cater to the sudden surge at a particular time of the day by having the storage of energy during the other time of the day when we don't have the maximum requirement of power. So basically you can actually bifurcate the power requirement into three main zones. One is the base load generation, one other one is the mid merit generation or the median load generation, and another one is the peak load generation. So on the basis of this load generation and on the basis of the demand which you are having on the prosumer side, it can very well be convincing or it can very well be understood that why we are speaking about peak shaving and why we are speaking about retrieving the energy from certain energy storage technology which will help us to generate energy and store it at that point of time and then later utilize it when we are trying to attempt for peak shaving. So I think this much of general concept of energy storage requirement is good enough to proceed further and understand what are the various technologies which we speak about when we go to low grade energy storage or when we go to thermal energy storage. Of course, this has already been spoken about. Like I spoke about the different time of the day when the power requirement is there, the different time of the year when you are actually having less power requirement in comparison to that of the other parts of the year. So basically it is the shifting of energy from one point to another when it is getting generated and where it is getting generated to when it is required and where it is required. So this type of mismatch of power generation and requirement actually helps us to understand more convincingly the requirement of energy storage. There are n number of ways through which this energy storage can be classified. I will not read them over here. So you can see that there are various technologies through which we can actually store energy. Today, we will concentrate more on thermal energy storage, which is the low grade energy, which is being stored in certain condition, in certain design aspect, and then we utilize it the other time when it is called for. So I will today discuss more about thermal energy storage. So now when I'm speaking about thermal energy storage, as I already mentioned, basically it is a low grade energy and it is having much better way of packaging it when we are speaking about the efficient way of storing the energy and retrieving it as and when it is required. And the same concept, as I was telling, that this thermal battery, this terminology is coined out from our basic concept of battery. But if I'm speaking about the concept of charging and discharging and storing, which is there in any energy storage, similarly in thermal energy storage also we are having these three concepts through which we can actually store the thermal energy and then we can retrieve it as and when it is required. So this slide pretty much shows the same concept of charging, storing and discharging of thermal energy over the period of time on which you are working to develop a particular thermal energy storage technology. Because there are classifications when we go in more details of thermal energy storage in terms of the physical storage or in terms of the temperature and the type of thermal energy storage concept which is utilized, in terms of the chemical storage concept, basically the exothermic or the endothermic reaction with which the energy can be stored or with the energy can be dissipated from that particular thermal battery. Today, my idea will be to speak more about latent heat thermal energy storage in comparison to that of sensible heat thermal energy storage. So when I'm speaking about latent heat thermal energy storage, basically the temperature of the system more or less is kept constant. There will be certain undulations which is because of the material constant, but unlike that of the sensible energy storage where there will be a temperature gradient through which you are actually storing the energy and then you are releasing the energy. Having said that, the concept of latent heat energy storage in terms of the energy density gives us more room when we are comparing it with sensible energy storage systems. Basically, the energy density will be much higher in comparison to that of the sensible heat energy storage system. I think this is very easy to comprehend. For example, if I'm speaking about the evaporation of water at 100 degrees centigrade, if you would have checked it in the steam table, if you would have checked it in any physics book, the amount of energy which is stored during that phase transition at 100 degrees centigrade is much higher in comparison to that of the energy which is stored or through which the heat is being gained when the liquid is at room temperature and you are raising the temperature to 100 degrees centigrade. And that's the main difference between the latent heat energy storage system and sensible heat energy storage system, where the energy density is out, why we are chasing this, why we are exploiting this technology, where we are more interested in latent heat energy storage system in comparison to that of sensible heat energy storage system. This slide pretty much gives you the information of how different energy storage technologies have developed over a period of time in terms of the technology readiness level. If I'm speaking about, and of course, the blue points are more on the electrical energy storage and the light green points are more on the thermal energy storage. So if I'm speaking about thermal energy storage, the easiest one which we can see is the rooftop flat plate collector with a small tank where we store the hot water and utilize it for various domestic purpose. In fact, that is the most common and most widely used latent heat, most widely used sensible heat energy storage system throughout the world. So if I'm speaking about the technology readiness level of that technology, it is quite high and it has been commercialized. But there are still some of the technologies, even on the thermal energy side, which has not taken its peak, which has not taken its momentum in terms of the technology. There comes the thermochemical energy storage system. But of course, this thermochemical energy storage system is highly efficient when we are comparing it with any other system where there is the main drawback with the thermal loss which is associated with the thermal battery. We will see that in the subsequent slides. Now, this is bit of on the thermodynamic side where I'm trying to appreciate the latent heat energy storage system on the basis of the temperature range. So it is a very common fact that if you are having a system which is at a very high temperature, say beyond room temperature is everything is high, but I'm saying high temperature something like 500 degrees centigrade. And if you want to tap the energy from such a high temperature to reach the dead state, which we call the thermodynamic dead state of say the standard room temperature of 30 degrees centigrade, and if certain energy storage or thermal battery is working at such a high temperature, and if you are maintaining the same delta T for another thermal battery which is working at reasonably low temperature. Let me just give you an example. Suppose you are having two systems, one is at 500 degrees centigrade and another system which is at 70 degrees centigrade, and let the dead state or let the normal temperature be 30 degrees centigrade. Now, if the two systems are being utilized for extracting thermal energy from them, and if we are maintaining the same delta T, say from 500 we are reducing the temperature to something around 470 degrees centigrade, so 30 degree, and from 70 degrees centigrade, say we are again dropping the temperature to 40 degrees centigrade, the delta T, although being constant, the quality of energy which will be there at high temperature latent heat energy storage system will be much higher in terms of the exergy or in terms of the available energy with which the quality of energy is being quantified. And that is the beauty of this high temperature latent heat thermal energy storage system, and that is the basis of utilizing this thermal battery at such high temperature. And of course, some of them are comparable with the electrical energy storage, say of lithium ion battery. In fact, we have done some comparison between lithium ion battery system as well as high temperature latent heat energy storage system, where we found that high temperature latent heat storage system works much better in comparison to that of the lithium ion battery system. Having said that, then why we are not marching towards it? You know, when we are speaking about high temperature, say 500 degrees centigrade, it is a big challenge to maintain that temperature at such a high level, because you should have a proper insulation, you should have leak proof arrangement of the silos in which you are stuffing the phase change material. So these are the design challenge. If we can overcome, then this high temperature latent heat thermal energy storage system can actually help us to store energy in a much efficient way when we are comparing it with high grade energy storage system or electrical energy storage system. So this is the takeaway from this slide. So I think I have mentioned about the phase change material and how at constant temperature the amount of energy which is stored is much higher in comparison to that of the sensible heating of a particular system. And when I'm speaking about a temperature which is much ahead or much higher than that of the lower room temperature, there the exergetic efficiency of the system becomes a very lucrative way of storing the energy. Having said that, if I have to speak about what is the research gap or what are the objectives with which this high temperature thermal energy storage system is to be designed, there are many physics related anomalies which has not been studied till now when we are trying to uh, capture the efficiency of this high temperature thermal energy storage system. And that's what we wanted to understand, how the physics is different for the high temperature latent heat thermal energy storage system and how they can be beneficial in terms of tapping the energy. For example, here I have highlighted about supercritical CO2 based Brayton cycle, which actually, if working at such a high temperature, say beyond 700 degrees centigrade, then the efficiency of the system, efficiency of power generation is much higher in comparison to that of any other working fluid which works in the same technology of Brayton cycle. So this is the thermohydraulics of an ultra high temperature phase change material. Basically, we have taken silicon as the phase change material. For common person, silicon, which is actually the component of the sand, and the silicon which is being utilized for developing the silicon based solar cells, so on. So basically we wanted to understand, can silicon which is having a very high melting point be utilized for this storing of energy or for this phase transition from solid to liquid when the melting takes place, how this entire system works as a thermal battery. So that was the whole reason with which we have done this analysis based design, where we have actually done the entire CFD analysis of silicon and having the boundary conditions being imposed so that we can raise the temperature of silicon at such a high temperature where it actually melts. So we have seen some interesting observation for silicon in comparison to that of other phase change materials, say solar salt or say any of the carbonates. Basically, one important characteristic of silicon is that the molten silicon is much denser in comparison to that of the solid silicon. And that's why once the silicon melts, it does not go up in the lighter molten state, it actually goes down in the heavier molten state, unlike any other salts which actually lightens up and goes up. So that was one of the anomaly which we actually characterized and found the comparison between some nitrates which is actually having a clockwise current being generated when it melts in comparison to that of silicon, where we are having an anti-clockwise current formation when it melts. And this is just because of the thermophysical property of silicon being different from that of other nitrates which are also at higher temperature. This is something which I just now mentioned about utilization of thermal battery, how it can be utilized for power generation in a more efficient way. So this supercritical CO2 is having the characteristics in terms of the best characteristics of a fluid when it goes to the viscosity, and the best characteristics of the gas when it to the density. So in that way, if we are utilizing supercritical CO2 being coupled with silicon battery, which is having the melting point beyond 1000 degrees centigrade, definitely this will be the game changer when we are trying to generate or harness power. So that was the main idea with which this high temperature thermal energy storage, latent thermal energy storage, has been coupled with a system where supercritical CO2 was the working fluid for the break cycle, and the entire study has shown us that it is having some promising features in terms of the efficiency, in terms of the tapping of energy at such a high temperature, where silicon can be used as the thermal battery. So these are some of the characterization which we have carried out in our lab. This will give you the idea what sort of facilities we are having at IIT Delhi. So basically the idea is to construct or synthesize the phase change material in the lab and then carry out the entire thermal characterization, the entire material characterization to understand how this thermal battery, when it is being packaged with ultra high temperature materials, can help us to design the system in a more efficient manner. So this is differential scanning calorimeter, which helps us to understand the heat absorbing, heat releasing capability of a particular phase change material. So that is being carried out in our lab. So this is the experimental setup where the thermal battery, which is having the nitrate of salts, basically the sodium and the potassium nitrates, in the ratio of 60 and 40% by weight. They have been utilized to make the phase change material with therminol as the heat transfer fluid, which is being passed through the annulus. And then we wanted to understand how the entire system goes for charging and discharging under various angles. So we actually change the eccentricity from vertical to horizontal with some intermediate angles, just to understand the efficacy of this thermal battery, which is being utilized for high temperature latent heat thermal energy storage system. These are some of the observations which we had, where we wanted to understand how the horizontal versus vertical thermal battery will have different efficacies in terms of the charging and discharging of that thermal battery over a period of time for different flow of the heat transfer fluid through that particular thermal battery. So I will not go into details of it. So coming to the summary, so I will say that this technology being challenged when we are comparing it with any of those high grade electrical battery. Of course, this can be utilized, but the main thing is how we can actually design that particular thermal battery in terms of minimizing the heat loss, how we can make the system more efficient when we are attempting to understand the orientations through which the system will be kept in terms of the convective heat transfer which is happening through the system. What should be the eccentricity at which the phase change material should be positioned in comparison to that of the heat transfer fluid which is being utilized for the charging and discharging. So there are many dimensions through which you have to optimize this thermal battery so that it becomes comparable to that of the high grade electrical energy storage system, which are basically the lithium ion batteries or any other chemistry of the batteries which we are actually speaking in terms of the high energy density for which it is famous. I will show you some other insights of the thermal battery, where we wanted to understand how this thermal battery can actually increase its efficiency in terms of reducing the charging time. So we wanted to understand, can there be some mechanical intervention on the thermal battery? Can there be some mechanical intervention on the phase change material based thermal battery, so that the overall charging time of that thermal battery can be some way or the other minimized? Now the question was, when I'm introducing some mechanical intervention, basically I am spending extra energy to make that system to reach a lesser charging time or to reach the entire saturation state at a faster pace. So for that, there should be some understanding, is it actually viable or not? So to the study which we have conducted, basically we have taken a mechanical stirrer and then we have stuffed the phase change material in the thermal battery. This is the cylinder, and the rating of this thermal battery was around 3.5 kilojoule, and the material which was utilized was D-mannitol. The phase change material which was utilized was D-mannitol. So basically the idea was to stuff the phase change material inside and then pass the heat transfer fluid through the annulus. Of course, the phase change material, once it gets melted, we wanted to stir the phase change material so that the entire phase change material becomes uniformly heated within a certain shorter period of time, so that the entire thermal battery gets charged for the tapping of energy. So that was the whole idea. And as I was saying, once we introduce some mechanical system, is the expenditure of energy. Just we wanted to understand, is this extra amount of mechanical energy which is being utilized to make the thermal battery uniformly heated, uniformly temperate, is good enough to decide upon introducing some sort of external mechanism of providing energy to stir it. So that was the whole idea with which the system was designed. And we found that there is, of course, like if the system is not having any sort of external stirring mechanism, then the time which is required for reaching the uniform temperature is around 1200 seconds more than the time when you are having a stirring mechanism being utilized. So in terms of the charging efficiency, when we found the comparison, irrespective of utilizing the extra energy for that stirring, we are having the charging efficiency getting enhanced by around 3 to 4% when we are comparing it with the system when there is no stirring. This time is actually reduced by nearly 1200 seconds when we are having the stirring mechanism in comparison to that of without stirring mechanism. So this is quite insightful to understand how a small change in the overall system dimensions, overall system design can actually help us to reduce the charging time and enhance the overall charging efficiency of the system. These are some experimental based study in terms of the confidence level and the uncertainty associated with this experiment. So I think the takeaway from this slide is regarding this reduction in the time by 1200 seconds when we are actually introducing this stirring based mechanism which is rotating at a 200 rpm. And if I'm speaking about the application, then this application can be for some non-conventional cooling system as that of a solar absorption system, solar absorption chilling system, where if you want the utilization of the solar energy being stored in the thermal battery using D-mannitol, then you can utilize this thermal battery to provide the cooling throughout 24/7 for the same system, which will not be operational when there is no solar energy. So that was the whole aim with which this was introduced. Now this slide actually shows the technology readiness level which I have already mentioned about. So globally, if I'm speaking, and what we are having in our country, so basically they are more or less at par with each other, both the sensible and the latent heat thermal energy storage system. So the technology readiness level is pretty much on the deployment or the commercial side in comparison to that of the thermochemical energy storage, where still the technology readiness level is at its very nascent stage. So these are some of the actual physical thermal batteries which are available pan world. So I have picked up some of the thermal batteries which are actually there in Australia, and these are the companies Climate Change, Vast Solar, and then there is 1414 degree in southern Australia. And of course I have picked one from Sweden, where they are actually using this latent heat thermal batteries, having silicon or molten salt, aluminium as the material to store energy and then utilize it for various power gen and process related activity. So I just wanted to highlight it so that you get the confidence that of course this is doable. Only thing which you have to keep it in mind are the design strategies, like the leakage or the heat loss which is happening from the thermal battery, and the orientation which actually helps us to enhance the charging of the thermal battery so that we can tap the energy as and when it is called for. So this is the status of the deployment of this thermal batteries. Now, this gives actually some idea of the thermal batteries which are their pan world, where we are having different solar thermal power generation systems, and we are having the thermal batteries with certain duration, and generally the duration will be ranging from 6 to 12 hours, but most of the time it will be around 7 or 8 hours. So you can see that when I'm speaking about the latent heat thermal energy storage system, so there are actually solar thermal power generation through central receiver tower technology, where this latent heat thermal energy storage system utilizing molten salt has been utilized. Having said that, in terms of utilizing ultra high temperature thermal battery where silicon has been utilized, there are only few examples which I just showed in the previous slide. This is regarding the operational projects of the central tower technology, the CSP concentrated solar power plant, which are available in India. So I think this is more India centric to give you the idea where this country is actually today in terms of utilizing the thermal energy storage and solar thermal technology for power generation. This is regarding the supply chain, where we are actually trying to understand how this technology can actually penetrate in the market or the supply chain of India basically. And we found that still it is in its very nascent stage, and there are a lot of challenges when we are trying to speak about the solar thermal technology in comparison to that of the solar PV technology. This is regarding the economics and planning. And as I was mentioning regarding lithium ion battery, when it is being compared with high temperature latent heat thermal energy storage, basically utilization of silicon, as I was mentioning. So you can see that in terms of the levelized cost of energy, we are having lithium ion storage technology. It is on bit higher side in terms of the Indian rupees. It is around 24 Indian rupees per kilowatt hour when we are attempting to compare it with the high temperature latent heat thermal energy storage system, where it is around 10 Indian rupees per kilowatt hour for the same deployment of 200 megawatt energy. So this economics or this techno-economics actually helped us to understand how latent heat thermal energy storage system can be comparable or can be deployable in terms of the techno-economics when we are comparing it with existing electrical energy storage system utilizing lithium ion storage technology. So this was quite a convincing number to make us convinced that this is having its own merits when we attempt to deploy it for the larger community. So these are the references. Basically, some of the references are from the work which we have done, and some of the references are from the work which we have actually, when we started our work, which we have actually read through to come up with this basic design of latent heat thermal energy storage system. These are the references. Thank you for your attention. So I am now open for questions.
Thank you, Professor Rakshit, for this insightful talk and emphasizing on the grid scale thermal energy storage. So, really, this type of energy storage plays a crucial role in transition to a more sustainable and resilient energy system. Now we understand. So, thank you so much, Professor Rakshit. So, now I would like to ask participants if you have any questions or any comments, please feel free to ask here.
Yeah, so I
Mm,
think I got
yeah.
one question.
Hmm.
It is saying, okay, so it is from the Vishal Sharma.
Yeah.
So it is regarding the utilization of phase change material and then to estimate, then to understand that what is the useful lifespan. So, and are they eco-friendly? Which material has the highest efficiency, and what is its value? So, thank you for this question. So, I will take one by one. So, basically, when I'm speaking about phase change material, today what I exemplified, it was silicon. So silicon, which is having a melting point beyond 1200 uh, degrees centigrade. So when I'm speaking about silicon, basically the efficiency is comparable to that of lithium ion battery, as you saw in terms of the energy density. So the efficiency, the round trip efficiency, can go beyond 80% if I'm speaking about silicon. And of course silicon is very eco-friendly, so that is also not to be worried about in terms of the carbon footprint. But having said that, if I'm speaking about of the other phase change material, say, yeah, I also spoke about D-mannitol, and then there are many other organic phase change materials. There are many other inorganic salts, for example solar salt, where the temperature is bit lower. Then in that case sometimes the question can be for making it eco-friendly or not, and that's where we are working at this point of time. So we are taking some biodegradable material, so that they don't have an impact on the ecosystem, they don't have the impact on the environment, but they have the same efficacy as that of the non biodegradable phase change material. So the main point of choosing a particular phase change material is the temperature at which it melts. So generally in terms of the lifespan, I will answer it. So when you are speaking about lifespan, so if I'm speaking about, say, there are phase change material which are utilized for building applications, like carbon 20 and icosan, carbon atoms 20 and icosan. So by rule of thumb it is said that if that phase change material can go through the resilience test of cyclability for 500 cycles, minimum for 500 cycles, then that phase change material will have its efficacy intact for next 10 years, over which you are deploying it in say some building applications in building envelopes. So basically that 500 number of cycle is something, sometimes we again extend it to 1000 cycles. So that's how we want to understand what is the resilience capacity of that particular phase change material, and we do the cyclability and find it that if the thermophysical property of that phase change material is intact for at least 500 cycles, if not 1000 cycles, I'm speaking about the thermal battery, then we say that we are rest assured that it will have its life for next 10 years when you are actually deploying it in the technology or in the system where you want to store the energy. I hope that lifespan question and yeah, the efficiency, I think I have answered mostly all. So
Yeah.
thank you for your appreciation. Thank you.
Yes, thank you so much, Professor Rakshit. I also would like to thanks our participants as well. So we really appreciate your time and commitments over here. Thank you, Dr. Rakshit,
Thank
for
you.
your
Thank
wonderful
you.
presentation and interaction with our participants. Now, we are moving ahead with our next session. So, our next part of the session is a student presentation. So, it is requested all DNG student to join the session by using the DNG presentation link, which is already shared with you all. So, thank you so much, all of you, and thank you, all presenters.
Thank you. Thank
Thank you
you.
so
We
much.
are
Yeah.
lucky.
Yeah, have
Thank
a
you.
great day.
Thank you. You all.